Welcome back to eCoreAcademy, everyone. My name is Anita Raj, and as you can see, today I'm bringing you all a new Biology 1 video. Recently, we ended our mini-series on the process of science, in which we talked about the scientific method, how to design an experiment, and then how to execute that experiment. Now we're actually going to be moving on into the units I described in my Introduction to Biology 1 video, which you should definitely check out. All of my biology videos are on a playlist on our channel, so please look at those first before coming to this video. In this video, we're going to be talking a lot about chemistry, and many of you are probably thinking, this is a Biology 1 course, why are we talking about chemistry? Well, we're not just going to be talking about chemistry, we're going to be talking about biochemistry. Biochemistry heavily involves carbon, and as many of you know, carbon is an element on the periodic table that is found in many living organisms. Many of you might be familiar with carbon used in like radioactive dating, where we trace the amount of carbon something that is dead, like a corpse or a fossil remain. We trace how much carbon that has, and then by seeing how much the carbon has decayed over the years, we can figure out how old that organism is. So even though things are dead, they still contain carbon. So what I'm trying to say is that everything that is living contains carbon. I have carbon in me, you have carbon in you, your dog has carbon, everything has carbon. And biochemistry focuses mainly on carbon because carbon has so many interesting chemical properties just because of the way it bonds. And that's what biochemistry, I want to say, is really based off of carbon. And just so you all know, the 6 main elements we're going to be focusing on, especially when we go to biological macromolecules, are going to be carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Those are the 6 main elements that are found in our 4 classes of biological macromolecules, which are carbohydrates, lipids, nucleic acids, and proteins. So that's what you're normally going to find. And that's why I think it's very important that we talk about chemistry and the way that these elements bond together, and how atoms bond together, so that when I show you actually the molecular structures and how these macromolecules look, you won't be confused as to why specific elements bond together, why a specific macromolecule acts a certain way. Like, for example, lipids are especially oils, are nonpolar, and you might not even know what the word nonpolar means. So I feel like it's really important that I go through this brief mini-series on biochemistry with all of you so that we all are up to speed about what we're going to be talking about in our first official unit. So in this video, we're going to be understanding matter. I'm going to be talking about atoms, show you the periodic table, and then talk to you about compounds and mixtures. And in the following videos, we'll go more into depth about types of changes like physical chemical changes, physical chemical properties, the structure of an atom, how an atom bonds, and further. So let's get started. But before I even get into the lesson, I would really appreciate it if you could pause, hit the like button, hit the subscribe button, hit the post notification bell, drop a comment down below, and share using our socials. It's all greatly, greatly appreciated. So on the first slide, we're going to be talking about the composition of matter. Whenever you hear the word composition, I know it might seem like a long and daunting word. Composition is pretty much just talking about what something is made up of. For example, I'm trying to think of something. Bread. Bread is made up of, a cake. A cake is a perfect example. A cake, the composition of a cake would be the eggs you used to make it, would be flour, would be milk if you added it, any food coloring you added, and any flavoring. It's pretty much what something is made up of. For example, as a living organism, I am made up of carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, and then I'm made up of all these other things that are the product that can form when all these six elements bond together. For example, I'm made up of water. I'm made up of carbohydrates, of lipids, of nucleic acids, of proteins. So that is what I am composed of. That is my composition, what I am made up of. So composition is what makes something up. And we'll talk about matter shortly. So first, I want to talk about what atoms are. So atoms are the building blocks of matter. Before I even talk about what atoms are, let's talk about what matter is. And I'm pretty sure many of you know what matter is, but do you have a very good understanding of it? So matter is anything in our known universe that has mass and that also has volume. Mass is pretty much, to put it in the most scientific way possible, it is an object's resistance to force. For example, something with a lot of mass, like let's say a bookshelf, will be much harder for you to push compared to something that has very little mass, like for example, a ball or like an exercise ball. So it really depends on how resistant that object is to being moved, to how resistant it is to a force that is applied to it. Um, Mass is also measured in the same unit as weight is. For example, many of you might use grams and kilograms to measure weight. Others might use pounds and ounces to measure weight. Mass is measured usually in grams and kilograms, and we use a triple beam balance. Usually, we use triple beam balances, and we also use scales to measure mass. And on the other side, we have volume. Volume is how much space an object takes up. For example, you probably know about volume from geometry. You probably studied volumes of cubes, of rectangular prisms, of right cylinders, of pyramids, of cones, and AJ's probably gone over that in our geometry course. Same applies to any living organism. You have to take up space. For example, I'm sitting in a chair right now. I'm taking up space in this area. So I'm a form of matter. Atoms are the building blocks of matter. So while I am matter, what actually makes up matter? So what makes me up? Well, like we said before, we have things like we have molecules like water, and we have macromolecules like carbohydrates, lipids, proteins, nucleic acids making me up. But if we break it down even more, what makes them up? Well, elements make them up. For example, the 6 main elements that constitute life: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. But if we take it down another notch, what makes up elements? Well, elements are represented by atoms, and atoms are very, very, very small particles. They're even smaller than your cells. And often you have to use like those electron microscopes to see atoms are very difficult to see. Let's put it that way. Atoms are the building blocks of matter. So atoms are what put together. Like if you want to think of it this way, like if you want to think of it like Lego pieces. Oftentimes you build with Legos to make a house or just anything in general. Think of atoms as those little bricks that you put together to build that final product, which is the house, which in this case is matter. Atoms are the basic chemical unit of an element that retains its properties. And in the next part, I'll talk about what an element is. They're found on the periodic table. But elements, if you want to think of it like, if you all remember when I explained to you that we build up in biology from the cell to the tissue, to the organ system, to the organism, to the population, to an ecosystem, you can think of it similarly in chemistry as building off of the atom. Then you have an element, then you usually have some kind of compound or molecule of sorts, and then you can eventually just build your way until you get to matter. So atoms are the simplest forms of an element that still retain its properties. So even if I have one atom, I can still say this is an atom of, for example, hydrogen. Hydrogen is an element you're all familiar with. I can say this is an atom, but it is representative of hydrogen. This is an atom, it's representative of oxygen. So while these atoms are so small, they still represent something bigger, which are these elements. If we break it down, if we go into the atom and we just look at more subatomic, sub means even lower if you want to think of it that way. So if we break it down even smaller, that's when you start losing the property of an element. So if I look at like the individual protons inside of an atom, then you start losing the actual property that why this element is special. So atoms do represent those elements, and if you look at things at the atomic level, it still retains the element's properties. And you probably were thinking when I was describing that, what is a proton if you've never heard of a proton before? Well, atoms contain subatomic particles. And like I told you, subatomic particles are particles that can just be found inside and around the atom that are even smaller than the atom. The subatomic particles include protons, which are positively charged subatomic particles. They're found in the nucleus of the atom. So if you know the nucleus of the cell, the atom has a nucleus as well, and that's where you'll find the protons. We have neutrons, which have no charge. They are neutral particles also found in the nucleus with the protons. And then you have electrons. These are negatively charged particles, subatomic particles. They're not found in the nucleus. They're found in orbitals. So while this might be the nucleus of an atom, and this is where you would find the protons and the neutrons, your electrons would just be spinning in orbitals constantly around your nucleus. And your nucleus is the densest part of the atom. Your protons and your neutrons have the most weight. Have the most mass. Sorry, they are what compensate for the atomic mass of an atom. If you don't know what atomic mass is, we'll be talking about it soon. And electrons are just so much smaller. I just forget what fraction of a proton they are, but they are so much smaller, but they are charged. So electrons will just be orbiting around this nucleus because electrons, remember, opposites attract. So the electrons are attracted to the protons in the nucleus. So while they will just not drift off and away from the atom, they will not touch the nucleus. They will just be going around in their orbitals, just constantly moving around the nucleus instead. Now let's talk about elements. So we start off with the atom, and atoms represent elements. Remember, atoms are the most basic unit of an element that still retains its property. Elements you can think of as the basic units of matter. So the best way I want to put this is think of something like weight. Weight is something we measure. We can measure weight. I just spoonerized that. We can measure weight in kilograms, in grams, in pounds, and ounces. Everything I told you before. Those are all units. Those are ways we measure weight. Similarly, elements can be used as ways to measure matter or describe matter. So elements are a type of matter. So they're like basic units of matter. When you put these elements together, you can form more complex pieces of matter. Elements, in essence, are pure substances that cannot be broken down by chemical means. And by chemical means, I mean if you do manage to break an element down, you're changing the element, so it's not retaining its properties anymore. So an element is a pure substance. If you want to think of a pure substance, this is the best way I can put it. Elements only contain one kind of molecule. One kind of particle. One kind of thing, if you want to think of it that way. So, for example, hydrogen is only going to contain hydrogen atoms. Oxygen is going to just only contain oxygen atoms. These are pure substances. We're not mixing them and diluting them in a way. If you want to think of it like pure water versus very muddy water. So muddy water you can think of as a bunch of elements mixed together to form like a compound or a molecule. Over here, we have pure water where we only have one type of element. Let's say we only have hydrogen atoms in this bottle of water. So think of elements like that. They are pure substances that cannot be broken down by chemical means. Chemical means include things like fermentation, burning, just things like that, maybe adding some other chemicals, just things that actually, we'll talk more about chemical changes in the next video, but things that actually change the properties, like the actual build of the atom. So I'll go over this quickly. An atom has a specific amount of protons in the nucleus, and the amount of protons in the nucleus determines what element that atom represents. So, for example, if we have a helium atom, and we end up if we have an atom, let's say, and we end up adding or removing its protons, we are actually changing the element it represents. And if that doesn't make sense, don't worry about it. I'll actually explain it on the next slide. We also have atoms with identical numbers. So they have atoms with identical numbers of protons. That's exactly what I was talking about. For example, a specific atom will only have a specific amount of protons. For example, oxygen. Sorry, that's not a good example. For example, I'll show you on the next slide what this means, but atoms of a specific element will only have a specific amount of protons. And I will show you on the next slide, I promise. And substances that can be bonded together, that means you can think of different atoms as of different elements being able to bond together. Like let's say we have a hydrogen atom, we have two hydrogen atoms, we have one oxygen atom. They can actually bond together. We'll talk about types of bonds. They can form H2O, which you all probably know as a water molecule. Before I move to the next slide, I want to show you this picture of an atom here in the middle that's glowing really brightly. You can see it's very dense. This is where you'll find the protons and your neutrons. And then over here, you see these spinny things going around the nucleus. These are going to be your orbitals, and these comet-like looking things, those are going to be your electrons just constantly moving around the nucleus in their orbitals. Next, let's look at the periodic table. As you can see, I actually, this is the exact one they gave me in school, and I actually annotated it, meaning I wrote all over it, and I tried to make notes to help guide you all. So here, we're just honestly just going to be talking about this periodic table. On the last slide, I remember telling you all that if we change okay, this is what I was trying to tell you on the last slide, and I wanted to do it with the periodic table. So the atomic number here, like for example, above this H stands for hydrogen. Remember, these are all chemical symbols. this is going your elemental symbols. So this up here above the H is going to be a 1. So this represents how many protons you can find in the nucleus. Similarly, if I come down over here to this P where my laser is, you have a 15. That means this is phosphorus, and in the atom it has 15 protons. What happens is the amount of protons in an atom cannot change unless you want to change what the atom itself is. So example here we have nitrogen. The atomic number is 7. So there are 7 protons in a nitrogen atom's nucleus. If we take away one of those protons, it actually becomes carbon. So it's going to become carbon because remember carbon has 6 protons. Now that atom has 6 protons in its nucleus if we take one away. If we add 1 proton to nitrogen's nucleus, we get 8 protons, and we end up getting oxygen. So see how we're actually changing the element, so we're actually changing its chemical properties. That's what I was trying to explain on the last slide. I'm going to briefly just talk about these different elements that you're going to find here. So first let's talk about this first. Over here I've written vertical equals period and horizontal equals group or family. So vertical obviously means going up and down like a line. So up and down, you call this a period. So example, if you just follow my laser, this is a period, this is a period, this is a period. Those are periods of the periodic table. Here we have horizontal, which is a group or family. So horizontal, think of like the horizon going across. So horizontal, horizontal, horizontal. These are what we consider groups or families. I feel like now that I'm in chemistry right now, but now we call them more so groups, but you can call them families. Both make sense. So just make sure you know what I'm talking about when I'm saying period or group or family. So this first, we're going to be breaking this down into groups or families. So this first column right here is the alkali metals. So this includes hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. So these guys right here, they have 1 valence electron. So if you think of it, so valence electrons electrons are going to be, remember, they go in orbitals around the nucleus, and there are actually different layers of them. So if you want to think of it like a cake, you have the nucleus at the very center, and then you have 1 ring around that nucleus, and then another one, and then another one. So obviously this is much more complicated than what I'm explaining, but the valence electrons are going to be the electrons you found at the very outside, the very outermost rings orbiting at the very farthest from the nucleus. So these substances right here, they have 1 valence electron, and they want to get rid of that valence electron, so they tend to get positive. So that's the characteristics of the alkali metals. We have alkaline earth metals right here. You have beryllium, magnesium, calcium, sodium, barium, and so on. And these guys right here, they are usually, when you find them, they're usually silvery or white. They also, what else did I want to tell you about them? Yeah. It's mainly that they're silvery or white. They're similar to the alkali metals in that they have 2 valence electrons, and you're probably noticing a trend. The period number is usually going to indicate how many valence electrons an atom has. So these also have 2 valence electrons. They also want to lose those valence electrons. We'll talk about that later in chemistry when we have a chemistry course, but don't worry about them now. Now we have this middle part right here, literally periods 3 to 12. I wrote this as alkali metals, but they're mostly your transitional metals. So metals have the characteristic of being conductive, meaning they can conduct electricity. They're malleable, meaning you can actually bend them in different shapes. So those are pretty much what you're going to be looking at here. So these are your alkaline metals. And then right here, you actually see I've drawn a line. This almost looks as a staircase. So remember it as a staircase because these specific elements I have here, such as boron, silicon, germanium, I can't even see that, and so forth. These are all your metalloids. So they have characteristics of metals, but they also have characteristics of non-metals. And usually, I think I read this somewhere, but they're usually like kind of yellowish in color, but they do have characteristics of both metals and non-metals. And finally, when we get to the right part of the periodic table, we're looking more so at the non-metals. So I even wrote it here, non-metals. So these are going to be a lot of your elements that are found in liquid state, in gas. I mean, not really liquid state, but gas state are kind of like a powdery state. They're not found like a metallic, like fully solid, like a metal would be. Here we have the halogens, which are period 17. The halogens are probably the most reactive elements on the table because if you look at the table, if these guys have just if you don't understand it, I will explain it when we do chemistry later on in a separate course, but they have 7 valence electrons. And every atom is looking to have 8 valence electrons. 8 valence electrons makes that atom stable. It's called the octet rule, because octet means 8. So these atoms right here, these elements, fluorine, chlorine, bromine, iodine, and so on, they are looking for that extra electron so they can fill their outermost ring. So they are just so, if I think of it this way, they're so desperate for that last electron, they're just willing to do anything. So they're very, very reactive. So they will always, they're called the halogens. And then lastly, we have the noble gases. These are all found in gas. They're all gases. They're all colorless, odorless gases, and they don't react at all. They're inert. That's what it means to not react, because they have a full outer shell. They have 8 electrons in their outer shell, except helium, of course. Helium is an exception. It has 2 valence electrons, but we won't talk about that right now. Helium is his own guy over there. But they have a full octet, super stable, don't usually react, are inert. Over here, I just want to show you. I kind of this element right here is lithium, so I kind of redrew the little block on the table, 3 lithium and the 6.94, so I can break down what each of these things mean. So the 3 up here is obviously your atomic number. Your atomic number tells you how many protons that element's atom has. Then you have Li. Li is your element symbol. As you know, all of the elements on the periodic table are abbreviated. For example, Li stands for lithium, and you see all the abbreviations on this table. And lastly, you have 6.94. 6.94 is the mass number. So this is pretty much the you're pretty much adding the amount of protons and neutrons found in this atom, and you're actually going to be averaging you're going to be averaging the mass numbers of many lithium atoms that you might find in the environment. Because believe it or not, we're going to be going into this later. They're called isotopes. So atoms in which the number of neutrons varies. So you would actually average the mass number of different lithium of different lithium atoms, and then you would find the mass number. Down here, I actually forgot about these 2. This is the lanthanide series and the actinide series. There are 2 more just series because they come off and they're just down here. Just acknowledge them. I really don't talk much about them. Here we have something called the S block, which is going to be these 2 columns right here. We have the D block, and then we have the P block and the F block. I wouldn't worry about them much. They're more so to help you write out the electron configurations of these different atoms. I just wanted to put it up there. So those are like the different sections of the periodic table. I know I went through that. I went through a lot of stuff, but don't worry if you don't get all of it. That's more chem stuff. But I just want to make sure you have that information if you're the kind of person who likes a lot of details. So now let's talk about compounds. So compounds are 2 or more elements that have been bonded together. So if you want to think of it this way, oxygen is a perfect example of. Actually, I wouldn't be going into examples. So why don't we just start that? So compounds are 2 or more elements that have been bonded together. So think of any 2 elements on the periodic table. For example, hydrogen might come up, or oxygen might come up, or nitrogen, or xenon, or honestly any element. And compounds occur when you bond 2 or more of those elements together. And these are going to be bonded by chemical means. And what I mean by that is that there are types of bonds that actually join 2 atoms together. Remember when I was talking about valence electrons? Well, they're important because valence electrons determine the bonding characteristics of an element. So it determines what other atoms of other elements that atom is going to be attracted to. The first example I have is the Ionic Bond, and you see NaCl. So NaCl is going to be, well, Na stands for sodium, Cl stands for chloride, which is a cation of chlorine. Don't worry if you don't know what that means. Just know this is sodium and chlorine. They're bonded together. And you might have heard of this NaCl because guess what? It's our table salt. It's the salt we use to season our food. So an ionic bond occurs when these 2 atoms, when the sodium atom and the chlorine atom, when the sodium atom actually gives up one of its electrons to the chlorine atom. The sodium atom wants to get rid of that electron and chlorine wants to accept it. That's the simplest way I can put it. So the sodium gives up an atom to chlorine, and they bond because of that atom of that electron that has been given up. I'm sorry if I kept saying atom, but electron that's been given up. And I'll actually show you a picture down here. Sodium is actually in period 1 of the periodic table. It has one valence electron and it wants to get rid of it so that it can get a perfect octet and it can be stable. So it gives up its one valence electron and it actually gives it to chlorine, which has 7 valence electrons. It's actually a halogen. It's one of those highly reactive elements. Sodium gives that up, and then as you can see, these dots right here, they represent the electrons that an atom has in its valence shell. So this chlorine is satisfied because it has its 8 electrons and a full octet. You can see there's a negative sign because this is negatively charged. There are now more electrons than protons because remember chlorine, I forget how many. Chlorine now has more electrons than protons. And here you have sodium. It has positive charge because it has more protons than electrons. Moving on to the covalent bond. So whenever you see covalent, a covalent bond is when electrons are shared. So instead of the ionic bond, electrons are given up or gained. Covalent bond is where the electrons are shared, and you typically have it between two nonmetals. So towards the right of the periodic table. So a covalent bond is usually, a typical covalent bond is where you have the electrons being shared equally amongst all the atoms in the compound. In this case, we have CH4, which is methane gas. Here's a picture of it. So remember that each element, just keep this in the back of your mind, when these elements bond, everything except hydrogen, boron, and beryllium, I believe. Every other element that you will find wants to have 8 electrons in its octet. So as you can see here, the hydrogens are happy because they just want 2 electrons. They'll be happy with 2. Carbon wants 8, and each of these lines here represent 2 electrons. So if you see, all the electrons are being equally shared in methane gas. When we look at polar covalent bonds, this is where we have a covalent bond in which electrons are shared, but they are pulled more towards one atom in the molecule than another. Perfect example of this is H2O, water, which we will be looking at in Biology 1. So I might as well introduce it to you now. Here's your oxygen atom and then your 2 hydrogen atoms. Remember, hydrogens just want 2 electrons, but the oxygen wants a complete 8 electrons. So what happens is the oxygen actually shares 2 electrons with this hydrogen here and 2 electrons with this hydrogen here, but it has 4 more electrons. So if you look at the whole molecule of water, this part of the molecule of water is going to be more negatively charged near where the oxygen is. It's going to be more electronegative. That's what we call it. Whereas this part of the atom is going to have a partial positive charge. So this is considered a polar molecule. We'll talk more about it later, but this is what we call a polar covalent bond. Next, I want to talk about how the ratio for each molecule is the same. So what this means is, for example, every molecule of water is going to have 2 hydrogen atoms and 1 oxygen atom to make that, this should not say molecule, it should say atom. 1 oxygen atom to make 1 water molecule. So for every water molecule, you must have 2 hydrogens and 1 oxygen. For every methane gas molecule, you must have 1 carbon and 4 hydrogens. For every NaCl molecule, you must have 1 sodium and 1 chloride. So they always combine in the same ratios. So that's compounds for you. Next, let's talk about mixtures really quickly. So mixtures are made up of 2 or more substances that can be separated by physical means. So they don't necessarily have to be elements. They can honestly be anything, any substance at all. They can be a molecule, a substance, a macromolecule, honestly anything, but they have to be combined in a way that I can separate them by physical means. What does this mean? Maybe I separate them by pulling them apart. Maybe I separate by boiling or freezing or all these other physical changes that I will be talking about in the next video, but they need to be separated by physical means. They're not chemically bonded together, so there are going to be no ionic bonds, polar covalent bonds, or covalent bonds. Substances involved retain their properties. So in that last part, the compounds, the different substances, when the elements bond together, they actually change. The properties of the elements will change, and the whole molecule that is defined as it has its own new properties. But in mixtures, the different substances that are involved, they don't change their properties. Some great examples I have for you are salt and pepper mixture and mixed nuts. So I don't have a salt and pepper mixture here, but I do have mixed nuts here. As you can see, I have different kinds of nuts. I have almonds, cashews, pistachios, all mixed together, but they're not chemically bonded together. I can just separate them if I wanted to. Think of it like they're just mixed together. That's what a mixture essentially is. And then what's the next picture I have? I'll go over that next. So a type of mixture is a solution. A solution is a type of liquid mixture with dissolved substances. So dissolved is pretty much when I drop, for example, when I drop something in, if I drop salt in water, what happens is the salt actually separates the sodium and the chlorine atoms. And you might not know why right now, I'll go over it later, but it's when something just dissolves, so it just separates inside another liquid. When we have a solution, whatever is being dissolved, for example, in this case, like the salt, that is considered the solute. What is being dissolved? Meanwhile, what is doing dissolving, in this case, water, because it's actually separating the salt molecules, that is what is called the solvent. And examples of this are lemonade and hot chocolate. So in lemonade, we have water with lemons in it, and when we drop sugar in there, it is getting dissolved in the water, because we can no longer see the sugar individually. We can't tell it apart from the rest of the lemonade. Same thing with hot chocolate. We're mixing milk with chocolate, and they're both kind of mixing together and dissolving. So that is another example of a solution. So that's all I have for you today. I hope you enjoyed the video. If you did, please give this video a thumbs up and also subscribe. Hit the post notification bell as well. Drop a comment down below and share using our socials, which are Facebook, Twitter, and Instagram. For any personal or business correspondences, contact us at eCoreAcademy@gmail.com. And please check out our website. It has a bunch of cool functionalities and is being populated day by day for all of you to use. Have a great day. Please reach out with any questions, suggestions. We love to hear from you. And I'll see you in the next biology video. Bye!